So, you ever stop and think about what's actually going on inside your phone or your computer? I mean, what makes that stuff so special? Well, it all boils down to a choice, a tiny little choice made by the smallest particles imaginable. We're going to dive into the world of the covalent bond and figure it all out.
Yeah, this is a great question, right? Think about it. On one hand, you've got a simple copper wire that can let electrons just flow like a river, enough to power a whole city. But then you've got a silicon chip, which is all about control, telling those same electrons exactly when to go and when to stop. That's how it holds data. The answer to this whole puzzle, well, it's way, way down at the atomic level.
Okay, so check it out. Here are our two main characters. On the left, that's a copper atom, and on the right, we've got silicon. At first glance, they look kind of the same, don't they? You know, a nucleus in the middle, electrons buzzing around it. But the real secret, the thing that changes everything, is hiding in plain sight. Look at that very last, outermost ring of electrons on each one. All right, to really get this, we've got to give a name to those super important outer electrons. They're basically the stars of this whole story. Let's meet the valence electron. So what exactly is a valence electron? Simple. It's just an electron hanging out in the outermost shell of an atom. I like to think of them as the social butterflies of the atomic world. They're the ones on the edge, the ones that reach out and interact with other atoms. They're responsible for all the chemical bonds, and that's what decides how a material behaves electrically. And this picture really shows us why they're so important. See that outer ring? That's called the valence shell. It's like the frontier of the atom. Because these electrons are the farthest away from the pole of the nucleus in the center, they're, well, they're a little bit looser. They're the ones most likely to get involved with other atoms next door. Okay, so this all leads to a rule that's almost too simple. Believe it or not, you can figure out if something will conduct electricity just by counting. Yep, just by counting the number of electrons in that outer shell. It's really that easy. So here are the rules of the game. If an atom has just 1, 2, or 3 valence electrons, well, it's way easier to just give those away than to try and find 5 or more to complete the shell. These guys are conductors. Now, on the other end, if you've got 5 to 8, you're so close to being full. So you're going to hold on tight to what you have and try to grab a few more. That's an insulator. But what if you have exactly 4? That's the big question. It's too much work to lose 4, and it's too much work to gain 4. This is the sweet spot. This is a semiconductor. This graphic just sums it up perfectly. You've got your conductors, which are like the generous givers of the atomic world. Then you have the insulators, the greedy takers, who just want more. And right there in the middle, you have the semiconductors. They're not givers or takers. They're looking for a totally different solution. They'd much rather just share. So let's focus on silicon and see how it solves this problem. Remember, it's got those 4 valence electrons, so it's stuck in the middle. But its solution is, well, it's brilliant. It's super strong, and it's basically the idea that made our entire digital world possible. We're talking about the covalent bond. Okay, so what is a covalent bond? It's really just a partnership. It's a deal. Instead of one atom just ripping an electron away from another, 2 atoms come together and agree to share. They each put an electron into the deal. The ultimate goal for any atom is to feel like it has a full outer shell, that magic number of 8 electrons. And sharing is the perfect way for these semiconductors to get that stable, complete feeling. And here's our hero again, the silicon atom. See? There's its nucleus in the center, and most importantly, count them. 1, 2, 3, 4 valence electrons in that outer shell. It's sitting right in that semiconductor sweet spot, totally ready to make a deal. And here's the magic in action. Look at that central silicon atom. It reaches out and links up with 4 of its neighbors. It shares one of its own electrons with each neighbor, and in return, each of those neighbors shares one back. So now, if you count the electrons that central atom gets to use, it has access to 8. 4 of its own and 1 from each of its 4 friends. Boom! It now has that stable, full outer shell it was looking for. Now, imagine that happening not just with 5 atoms, but with billions and billions of them. What you get is this beautiful, perfectly ordered structure called a silicon crystal. Every single atom is locked tightly in place, totally content, sharing electrons with its neighbors through these super strong covalent bonds. And here's the kicker. Because everyone's happy and all the electrons are locked up in these bonds, there are no free electrons to just roam around. And that's why pure silicon, in this perfect crystal form, is actually a really bad conductor of electricity.
All right, we've gone from individual atoms all the way up to a crystal lattice. Let's boil this all down into a super simple study guide so we can see everything side by side.
And here it is, plain and simple. Conductors, they've got 1 to 3 valence electrons, and they're happy to give them up. Insulators, they've got 5 to 8, and they're holding on for dear life or trying to grab more. And then there are semiconductors, with exactly 4. Their tendency is to share with their neighbors. It's amazing, right? That one simple difference, giving, taking, or sharing, is literally the difference between a copper pipe and the microprocessor in your laptop.
But this leaves us with one last massive question, doesn't it? If these covalent bonds are so strong and they lock all the electrons in place, making silicon a terrible conductor, then how in the world do we get those electrons to move when we want them to? How do we create the ones and zeros, the logic, inside a computer chip? Well, that's where things get really interesting.